This is a video for AQA Mechanics, Impulse and Momentum section 2.3, where we're looking at successive impacts of spheres. Well, as the title suggests, quite often we're asked to consider when one impact then leads to a second impact. You'll remember that in each of the separate impacts we still have Newton's law of restitution and conservation of momentum. Here we have three masses, A, B and C, that are moving at 7 meters per second, 3 meters per second and 3 meters per second respectively. You can see that A is going to catch up with B and collide, so there's going to be a collision between A and B. We're told that after that collision, A goes on to move with a velocity of 3 meters per second and B with a velocity of 5 meters per second in the same direction. B is now moving at 5 meters per second, so will catch up C, so there will be a second collision. We're told further that the coefficient of restitution is the same in both collisions, and we have to show that no further collisions will occur and to find the total loss of kinetic energy. The first thing to do then is to consider this first collision to see if that helps us to find the coefficient of restitution. Well, we know that the coefficient of restitution E is given by the speed of separation divided by the speed of approach. So in this case, E is going to be equal to the speed of separation. So afterwards they're separating at 5 minus 3 with a separation speed of 2, and the speed of approach is 7 minus 3, which is 4. So that gives us a value of E equal to 1/2. Now we've got that value of E, we can go on and look at the second collision. So now we've put in two unknowns, because afterwards we've got the velocities of B and C, both of which need to be found. Well, we can do that because we've got two equations, one for the coefficient of restitution and another for conservation of momentum. So considering first of all the coefficient of restitution E, we know that that is equal to 1/2, and we know that the speed of separation will be Vc minus Vb, and we know that the speed of approach is 5 minus 3, which is 2. So from this we get that Vc minus Vb is equal to 1. So that's one equation connecting the velocity of B and the velocity of C. Conservation of momentum is the second equation that we can use, and of course we need the momentum before impact. Which is B of mass 2 moving with velocity 5 to the right, and C of mass 1 moving with velocity 3. So that's the momentum before, and the momentum after impact we've got 2 Vb plus 1 Vc. So therefore our second equation is 2 Vb plus Vc momentum afterwards is equal to the momentum before, which is 10 plus 3, which is 13. So now we have a pair of simultaneous equations which we can solve. So if we do equation 2, take away equation 1, that will give us 3 Vb is equal to 12, and therefore Vb is equal to 4, and Vc must be equal to 5. So the velocity of B is 4 meters per second and the velocity of C is 5 meters per second. So now we know the velocities of all the objects after the second impact. And we can see that the velocity of C is greater than the velocity of B, which is greater than the velocity of A, and that means there will be no further collisions. We're also asked to consider the change in kinetic energy, so that's half mv squared. So if we look at the kinetic energy at the end, we've got a half times 1 times 3 squared, plus a half times 2 times 4 squared, plus a half times 1 times 5 squared. And we want to subtract from that the initial kinetic energy, which is a half times 1 times 7 squared, plus a half times 2 times 3 squared, plus a half times 1 times 3 squared. And that is 9 over 2 plus 16 plus 25 over 2. Take away 49 over 2 plus 9 plus 9 over 2, which is 33 minus 38, which is minus 5. So the kinetic energy lost is 5 joules. That concludes this video on successive collisions. In the final video in this section, we'll be looking at impacts with a smooth plane. So, for example, when an object is falling onto a smooth table and bounces several times.